All right, Math 6620. The purpose of this video is to start investigating something called logistic regression. And the purpose of logistic regression is to predict the probability of group membership where our dependent variable is dichotomously coded. Now, what I mean by dichotomously coded, it's typically coded as this or that. So there are two groups essentially, this or that, lived, died, succeeded, did not succeed. Again, some group membership that is dichotomous. And we can predict this using a set of predictors, and the predictors can be quantitative or categorical, so there's no restriction. So it might make sense that we would approach, and we just finished multiple regression, simple linear regression if there's one predictor. So it may make sense that we would want to continue using the techniques that we learned previously. Well, we don't, because the reason is the logistic regression model will look something like this, where again, we don't have any measurements from 0 to 1. The observed dependent variable was either, not what we're measuring, or it was what we were measuring. So a linear model is not appropriate because number one, it would predict probabilities, for example, up in here and down here that are less than 0 and greater than 1, and we all know that probabilities have to be between 0 and 1. So what we do instead of fitting this model or fitting this dilemma, if you will, with a linear regression model, we use what's called a logistic regression model. And it kind of looks like an S shape. So it models the not cases in a similar fashion with the cases, the positive cases. So what the logistic regression model will estimate, and let's just say we're looking at, I think sometimes it's easier to examine a model like this in terms of using kind of real life variables. So let's assume that the dependent variable here is the probability of passing or not passing a class based on an ACT score. And let's just say that the ACT score has been dichotomously coded as well. It doesn't have to be as 24 or lower and 25 or higher. Now, we want to focus on what is coded as 1 for X and Y. So let's say that 1 is passing the course for Y and X equal 1 is 25 or higher on the ACT for the predictor. So what we examine is we examine the probability of passing status when passing status is passing, given that the ACT score is 25 or higher. That is written as the probability of success, if you will, probability of passing, if we have an ACT of 25 or higher. So for any level of ACT, again, as it's dichotomously coded, 24 or lower, 25 or higher, we can predict the probability of passing using logistic regression model. Now, it's also true if we just use ACT as a quantitative variable, 18, 19, 20, 21, like that, it'd be the same thing. We would still have the probability of passing status, in this case, if it's coded 1, of being passing, given their ACT score as a quantitative measure. So in general, how should we proceed in examining and modeling this relationship? So what we have is we have the probability of X is just essentially the probability that Y is equal to 1. Again, I can't stress enough that the focus has to be on a particular level of your dependent variable. And in general, it's what we call, I usually refer to it as like successes and non-successes. So I define my success. In this situation, this example, it would be passing the class. If we were examining, maybe we work for an ER in a hospital, and patients come in with all these different particular measurements. And in this case, we're examining whether or not the person lives or dies. I would think a success in that case would be lives. But again, you can frame it either way, just depending on the design of your experiment. Or design of your study. So anyway, we would have the probability that y is equal to 1, however we set that up, given a particular value of x. So we're looking at the relationship between the probability of x and x. So the first guess, again, an intuitive one, it's not true, but an intuitive one, is to calculate the probability of x with a linear function. Again, we can't do that. We can't do that because some probability values would be predicted to be less than 0. Some probability values would be predicted to be higher than 0. And again, probabilities must be between 0 and 1. Second guess is this logistic function so that the outputs are between 0 and 1. And what this looks like is we can calculate the probability of x by exponentiating the linear function. So taking e to the linear function over 1 plus e to the linear function, which turns out this variable will be S-shaped, and the obtained predicted probabilities will be between 0 and 1. So exactly what we want. So with a little bit of algebra, we can take, we can manipulate the probability of x equals e raised to the b0 plus b1x over 1 plus e raised to the b0 plus b1x. Just a little bit of algebra, and again, this is not a difficult task. We can isolate the e raised to the b0 plus b1x term and see that it is equal to the probability of x over 1 minus the probability of x. Well, it turns out this is a convenient manipulation because it gives us something, which I call a nice result here, as the odds ratio. And odds ratio make the coefficients much easier to interpret than the log of the odds ratio, as I will point out here in just a second. So a little bit about odds ratios. Odds ratios will range anywhere from 0 to infinity. For an example, if we have, and again, low odds ratios come from low probabilities. Higher probabilities give us higher odds ratios. So for example, if p is 0.01, very low, we can see that the odds would be 0.0101, much closer to 0. If we have a high probability, in this case 0.98, we can see that the odds would be 49, which is obviously getting relatively higher. Now, so what we can see is we have that the odds on the left is equal to e raised to the b0 plus b1x. And we're just looking at one predictor here, but this can be generalized to where we have multiple predictors, as we will find out. So we can take the log of both sides. So if we take the log base e, and one thing, when you've reached, I don't know, kind of a higher level stats study of stats, log is just known to be the natural log. Typically, log is what base 10, not once you get to this level. Log is implied to be the natural log. So if you take the natural log of both sides, the natural log of e raised to the b0 plus b1x is just the exponent. And then on the left, we have the natural log of the odds ratio. And we call this the legit function. Now, remember, and if you take my math, I believe I covered this in 5500 or maybe 6500. So if you take those classes from me, we'll dive into this phenomena much deeper. But remember, the population model contains the coefficients beta 0, beta 1, and we collect our sample data and calculate a B0, B1 to approximate these two values. And this is done through what's called a likelihood function, not a least squares function, as we do with a linear or multiple regression model. And what we do is we find the values of beta 0, beta 1, which optimize this, again, maximum likelihood function. So we find the values of these that find an optimal value for this expression. Let me get out of this. I want to run through just very quickly an example. So let me pull up R, and I've already pulled it, an example up in R, and ran some commands and made some comments. So the data set that we're using here is called admit rank, and there's an admit status. 1 is the student was admitted. 0 is the student was not admitted. There's a GRE score, which is just easy to explain, right? GPA, I think, ranges from, I don't know, it's on a 4.0 scale. And then we have rank. So the first thing I have to look at is I look at my dependent variable. So I would like to predict the probability of being accepted, being admitted into this program based on the student's GRE, their GPA, and their rank in the college undergraduate program they attended, they completed. So the first thing I need to do is I need to make sure that admit is being seen as a factor and not zeros and ones. So I run the command, is this a factor? It says false. I really don't know why I did this because this didn't accomplish anything at all. So I ran this again, no idea why. Let's get to something that actually does make a difference. Here I created a new variable and I forced admit to be a factor. So my new admit F is, well, this is interesting because I used admit in the model. So I need to check that out. Maybe there's something in R that, okay, that's interesting. In fact, let me go ahead and do this because there's not much need in talking about this, the output. If so, it turns out the values are the same. So interesting. So I guess what happens is when you run the command, the GLM command, and you type family equal binomial behind the scenes, it will force the dependent variable in a factor. So in other words, all the stuff I did right here was completely meaningless. But I still think it's a good habit to get into when you have a variable that's consists of numbers and you want it to be treated as a factor. I still think it's a good idea to force it into a factor. So we'll proceed with the model. What we do is we run the GLM, the General Linear Model command. So here's my dependent variable, my set of predictors, and again, you must include family equal binomial to force the GLM command to run a logistic regression model. So when we get our output, we'll see that we get 4 columns. We get our coefficient estimate. Think of this as B0, this is B1, this is B2. More about this in just a second. The next thing we get is our standard error. What I look for there is I look down my standard errors and I want to see that these things are pretty consistent. If I get an extremely large number, it could represent an issue. But I'll put up a video, either the next video or a couple videos later, on testing assumptions and what happens when the assumptions are violated. The z-value is a typical z statistic. So z negative 4.205 is residing in a normal distribution, mean 0, standard deviation 1. Next thing I do is I start looking at the p-values, and they are all statistically significant at the 0.05 level. So it appears that taking our predictors one at a time, which is all we can do. We can't make any statement about our model yet. We can just make our statement about our predictors. All of our predictors are statistically significant. Now, what happened right here, you'll notice that when I come down here to table and look at rank, you can see that there were 4 ranks. The bottom 25%, which I would call the 25th percentile, the 25th to 50%, which I would call the 50th percentile, 50 to 75%, and of course 75% and above. Now, what it did, it will create dummy variables. And dummy variables are if we have a categorical predictor with k levels, we have to choose a reference category and then choose k minus 1 dummy variables from which we can make comparisons to the reference. Well, you can see the one that is missing here is the 25 to 50%. But I didn't want that. I wanted the reference to be the bottom 25%. So I have to re-level rank and reference the bottom 25% as my reference category. And I just renamed it rank. So from here on out, rank will be labeled as the reference bottom 25%, and the other 3 will be our dummy variable comparisons. So I rerun the model with rank in it after resetting the reference, and I get a slightly different model. Now look what happens. What I've set as the reference category, bottom 25%, is not included in the output. The reason is that's the reference category. It takes the other k minus 1 levels of the categorical predictor and compares each one of these to the bottom 25%. Now, what do these values mean? For example, let's just go to GRE. What does the 0.084 actually tell us? This tells us that for each unit increase in GPA, the log odds of getting admitted increase by 0.80. And I kind of make a joke here, like say, well, what does that mean? I think it's very, very difficult, even someone with a lot of experience in logistic regression, to interpret what it means to increase your X unit 1 unit, or your X variable 1 unit, and then analyze the change in the log odds ratio. Well, it turns out that there's a much simpler and actually much better way to interpret that. If we'll take the 0.80 and exponentiate it, so in other words, take e raised to the coefficient value. So I'm going to take e raised to the 0.804, which in R is performed by EXP 0.804. I get 2.23. This makes the interpretation much easier to understand because it gets it out of the log odds and just focuses on odds ratios. So I can say here the controlling for the other predictors in the model, the odds of being accepted, not log of odds, just the odds. By exponentiating the coefficient, we change the focus from log of odds to the odds. So the odds of being accepted increase 2.23 times for each unit increase in GPA. Now, R knows how important finding it knows how important it is to be able to exponentiate the coefficients of the model in interpreting. So it makes it really easy for us to do this for all of the predictors just by going EXP model $ coefficients. And you can see the GPA, as we kind of forced earlier, turns out to be 2.23, just as we said. So what I can say here is controlling for the other predictors, the odds of being accepted are 2.212 higher for students who, that should be rank, not tank, rank in the bottom 25%, than for students who rank in the 75%, right? That's the EXP of the coefficient. But I think sometimes when odds ratios are less than 1, it's kind of hard to interpret that. So another way of saying that is the odds, again, controlling for the other variables, the other predictors, the odds of being accepted are 4.72, 1 divided by 0.212, higher for students who rank in the top 75% than those who rank in the bottom 25%. I can reverse the wording and compare the top 25% to the bottom 25% just by taking the reciprocal of the odds ratio. So I think it's much easier. So you have almost if you're ranking your again controlling for GPA and GRE score, uh, you have almost the odds are almost 5 times higher for you to be accepted into this program if you rank in the top 75% versus the bottom 25%. So again, this is just where I kind of tested out the admit F versus the admit. So that's pretty irrelevant. So anyway, we're going to dive into logistic regression a lot more, but I just wanted to kind of get the ball rolling, let you see what's in store for the rest of this lesson. All right, take care.